Welcome to the deep dive. If you've ever found yourself just staring at a mountain of information, maybe prepping for a big meeting or, trying to quickly get up to speed on a new field, you know how overwhelming that can feel. Our mission today is to give you a powerful shortcut because we're taking a deep dive into something truly foundational in the world of data. Batch processing. We're going to unpack why these systems are so powerful, how they actually work, and what they do for us. I mean, from building the search engines you use every single day to powering the recommendation systems that somehow know what you like. And, well, you might be very surprised by where some of these really big ideas actually came from.
Oh, it's true. Batch processing is a critical, often kind of hidden building block for creating reliable, scalable, and maintainable applications. It's been central to data processing for far longer than most people realize. Its roots stretch way back, even before digital computers, believe it or not. Yet it remains incredibly relevant and, frankly, powerful today.
Okay, let's unpack this then. It's easy to think of data systems as these always-on, instant response machines, like you request a web page, check your bank balance, that sort of thing. But that's really just one side of the coin, isn't it? There are actually three core ways systems handle data. Could you maybe give us the quick overview?
Absolutely. So first, you've got services, often called online systems. These are designed for quick, individual requests where a user is typically waiting, right? Response time is absolutely everything here, and availability is key. Think of your web browser making a request, or maybe an app calling a remote API. That's a service. Then there are batch processing systems, which operate, well, offline. They take a large, usually bounded amount of input data, run a specific job to process it all, and then produce a completely new output data set. Now, these jobs can take minutes or hours, even days sometimes. There's no user just sitting there waiting for an instant response. They're usually scheduled periodically, maybe once a day, maybe once a week, and their performance, it's measured by throughput, how efficiently they can crunch through a certain volume of data. This is our main focus today. And finally, there are stream processing systems, sometimes called near real-time. They're kind of a hybrid. They consume inputs and produce outputs like batch systems, but they operate on events shortly after they happen, so they offer much lower latency than batch. Stream processing actually builds upon a lot of the concepts we'll dig into today, and it's definitely a deep dive for another time.
That's a really clear distinction. Thanks. And what's particularly fascinating, I think, is that while batch processing feels so technical and modern, almost, cutting edge, its roots actually go way, way back. It really feels like history repeats itself here.
It absolutely does, yeah.
Yeah.
Long before digital computers, even before the transistor, you had things like punch card tabulating machines. Think of the Hollerith machines used way back in the 1890 U.S. Census. That was a semi-mechanized form of batch processing. They'd take stacks of cards, each card basically a data point, and crunch them to compute aggregate statistics. And then, fast forward to 2004, when Google published MapReduce, which was this groundbreaking framework for distributed data processing. Well, the design of MapReduce bears this uncanny resemblance to the old electromechanical IBM card sorting machines that were used everywhere for business data processing in the 1940s and 50s. It's just a powerful reminder that these fundamental ideas often resurface, just in new technological wrappers.
So, okay, to really get the DNA of modern batch processing, we need to go back to a surprisingly simple yet incredibly powerful starting point, the Unix philosophy. It feels like the wisdom from that era still shapes so much of what we do today, doesn't it?
It certainly does, yeah. That philosophy was articulated so well by Doug McElroy, one of the inventors of Unix pipes, way back in 1964. He famously said, "We should have some ways of connecting programs like a garden hose screw in another segment when it becomes necessary to massage data in another way."
Mm.
That simple, like, plumbing analogy, it really stuck, and it guided the design of one of the most enduring operating systems ever.
Right, the garden hose. Let's make that tangible. Consider analyzing web server log files. Imagine you have an Nginx log file. Each line is just a single request to your website. And a single line can contain a ton of info, the client's IP, the timestamp, the URL they asked for, the status code, even their browser. It's just this long string of text. Seems kind of unstructured at first glance.
Exactly. Now, if you wanted to find, say, the 5 most popular pages on your website from that seemingly unstructured log file, .in, you could string together a few simple Unix commands. You'd start with cat varlan ginsaccess.log just to read the whole file, simple enough. Then you'd pipe that output, send it straight into awk, print $7. Awk is great for text processing, and here it just pulls out the 7th field from each line that's your requested URL. Next, you'd feed that list of URLs to sort, which, well, it sorts them alphabetically. After sorting, all the identical URLs are conveniently right next to each other, right? So unique match can then just zip through and count how many times each unique URL appears. Then at the second sort, idle resorts those counts in reverse numerical order, putting the most popular pages right at the top. And finally, HeadMyGen5 just grabs you the top 5 lines. Done.
And the output is incredibly clean, right? Something like 4189 favicon.ico, 3631 2 euro 3 euro 524 son dash blogpost.html, and so on. It looks almost deceptively simple, but it's potentially processing huge amounts of data behind the scenes.
Precisely. This chain of commands, even though it might look like a cryptic incantation if you're new to Unix, it's remarkably powerful. It can process gigabytes of log files in seconds, giving you pretty immediate insights. And it's surprisingly easy to modify, too. Want to ignore CSS files? Just tweak the awk command a bit. Want to count the top client IP addresses instead of pages? Just change that field number you're extracting. Simple.
But that's the magic, isn't it? Why is this chain of seemingly simple commands so effective? What makes this whole Unix philosophy so enduring?
Well, it really comes down to a few core principles described eloquently way back in 1978. The first is, make each program do one thing well. Think about sort. It's an excellent sorting tool, probably better than most library sorts you'd find, but its real power is only unlocked when you combine it with other tools, right? Second, expect the output of every program to become the input to another as yet unknown program. This basically means programs shouldn't clutter their output or insist on complex, proprietary formats. They should speak a common language. Usually that's plain text. Third, design and build software to be tried early. Throw away clumsy parts. This encourages rapid prototyping, incremental iteration, build something simple, test it, refine it. And finally, use tools in preference to unskilled help, which is really all about automation. When you look at this approach, automation, rapid prototyping, iteration, breaking down big problems into small composable pieces, it sounds remarkably like, Agile and DevOps movements of today. It's quite striking how little has really changed in 4 decades in terms of that fundamental software engineering wisdom.
The key thing enabling all of this is what we call the uniform interface. In Unix, that interface is basically a file, or more accurately, a sequence of bytes, usually treated as ASCII text. This simplicity is what allows such different programs to be plugged together so easily. Now, it's not perfect. Using print $7 to get a URL isn't as readable as having a named field, sure. But its effectiveness decades later is just remarkable. You can't easily, pipe the contents of your email account and your online shopping history through some custom analysis tool into a spreadsheet and post the results to a social network in the same seamless way. That level of composability is still pretty rare outside the Unix world.
And that leads to that powerful idea of separation of logic and wiring, right? Programs don't need to know or even care if their input is coming from a file or a keyboard or the output of some other program. They just read from standard input right to standard output. This flexibility lets you combine your own custom programs with standard OS tools, plugging them into pipelines however you need. It sounds incredibly empowering.
It truly is.
Yeah.
And another huge benefit is what we could call transparency and experimentation. See, Unix commands usually treat their input files as immutable. They don't change the original data. This means you can run commands over and over, experimenting with different options without ever messing up your original logs. And you can stop a pipeline at any point, pipe the output into less or something, and just visually check it. Is this what I expect? That debugging capability is incredibly valuable for rapid development. You can even write the output of one stage to a temporary file and then restart the next stage from that file, avoiding a full rerun if something goes wrong later. These tools are blunt, yeah, but they are incredibly useful for just trying things out and quickly iterating on ideas.
Okay. So Unix tools are amazing for a single machine. Processing gigabytes in seconds, great. But when we start talking terabytes or petabytes of data spread across potentially thousands of machines, that garden hose analogy suddenly seems a bit small. How do you scale that fundamental idea up?
That's precisely where MapReduce enters the picture. Think of MapReduce as a system that basically takes those core Unix principles and applies them to a distributed environment across lots of machines. Like Unix tools, it's a fairly blunt, kind of brute force, but surprisingly effective tool for dealing with massive data sets. A single MapReduce job is sort of comparable to a single Unix process. It takes one or more inputs and produces one or more outputs, crucially without modifying the input or having other side effects. But instead of standard input and standard output, MapReduce jobs read and write files on a distributed file system. Most commonly, that's HDFS, the Hadoop Distributed File System. HDFS is an open-source reimplementation of the Google File System, or GFS. And HDFS, importantly, is based on this shared nothing principle. This means each machine in the cluster operates independently, its own disks, its own memory, and they just rely on the network to communicate. No fancy specialized storage needed. This is what allows it to scale so cost-effectively using just commodity hardware. There's a central name node that keeps track of where all the file blocks are, and a daemon running on each machine exposes a network service, creating one giant file system view from all the individual disks. And to handle failures, because machines will fail, file blocks are replicated on multiple machines. It's similar in concept to RAID, but distributed across the whole cluster. HDFS has scaled to, well, tens of thousands of machines and hundreds of petabytes of data at a significantly lower cost than traditional dedicated storage appliances.
All right, so we have this massive distributed file system. How does this distributed version of Unix actually work then? Let's take our log analysis example again. How do those simple Unix commands translate into a MapReduce job?
Okay, so a MapReduce job typically executes in 4 conceptual steps. First, it reads the input files. The framework automatically breaks them into logical records for our log file. Each line is a record. Second, it calls a mapper function for each one of those input records. This function extracts key-value pairs. So in our log example, this is like the awk print $7 part. It extracts the URL as the key, and maybe just a placeholder 1 as the value, let's say. And importantly, these mappers run independently in parallel across many different machines. Third, the framework sorts all the key-value pairs by key. This is an implicit but absolutely crucial step handled automatically by MapReduce itself. It's just like that first sort in our Unix pipeline. All the values for the same key get brought together. And then finally, fourth, a reducer function iterates over those sorted key-value pairs. It combines the values for each key. This is similar to our unique C step, counting how many times each URL, the key, appeared by summing up those 1 values. The real power, though, comes from the distributed execution. MapReduce parallelizes this whole computation across potentially thousands of machines. Mappers and reducers operate on just one record at a time, conceptually. The framework handles all the complex data movement, coordination, failures, all that stuff. And the scheduler is clever. It tries to run the mapper tasks on the machines that are already storing the replicas of the input file blocks. This is called putting the computation near the data to minimize network traffic, which is often a bottleneck. After the mappers finish producing their key-value pairs, this process called the shuffle kicks in. This basically partitions the mapper output based on the key, usually using a hash of the key to decide which reducer it goes to. It sorts those partitions locally on the mapper's disk and then copies them over the network to the appropriate reducers. The name shuffle is a bit misleading, actually. There's no randomness involved. It's a very deterministic process designed specifically to bring all the data for a particular key to a single reducer. The reducers then merge these sorted files coming in from all the mappers and process all the grouped records for a given key together.
Wow, that's quite a complex dance of data moving around. But okay, what if your analysis needs more than just one map step and one reduce step? Say you need to do multiple stages of processing. That gets us into workflows, right?
Precisely. Yeah, it's very common to chain MapReduce jobs together. The output of one job becomes the input for the next one. The Hadoop framework itself doesn't really have built-in support for this direct chaining like Unix pipes do. It's usually done implicitly, just by referencing HDFS directory names. So job A writes its output to a specific directory, and then job B is configured to read its input from that same directory. It's less like Unix pipes, which kind of stream data directly, and more like writing intermediate results to temporary files between commands. Now, to manage these dependencies in complex flows, workflows of 50 or even 100 MapReduce jobs are not uncommon for something complex, like building a recommendation system. Various workflow schedulers have been developed. Tools like Uzi, Azaban, Luigi, Airflow, Pinball. Their job is to orchestrate these sequences of jobs, make sure they run in the correct order, handle retries if something fails, that kind of thing. And higher-level tools like Pig and Hive were also created to automate the creation and management of these multi-stage workflows, hiding some of that underlying complexity.
Okay, let's zoom out just a bit again. One of the trickiest things in data, generally, is combining information from different sources, doing a join. How does batch processing handle that, especially when you don't have those traditional database indexes you might rely on in other systems?
That's a great question, because batch systems like MapReduce, they typically perform full table scans. They read the entire content of all the input files involved. This is incredibly efficient for doing analytics over massive data sets. But yeah, it's not designed for quick single record lookups like you'd use an index for in a traditional database. So when we talk about joins in batch processing, we're really talking about resolving all occurrences of an association within a very large data set all at once, rather than doing individual lookups one by one.
Right. Let's use a common example. Imagine you're trying to figure out which web pages are popular with specific age groups. Your web server logs have the user IDs, but they don't have the user's ages. That user profile info with the age is sitting in a separate database somewhere else. Now, the simple approach of just looking up each user ID in that remote database as you process the logs, well, that would be incredibly slow, right? It would probably overwhelm the database, and worse, it could make your batch job non-deterministic if that remote user data changed while the job was running. So what's the better way?
Yeah, that's generally a really bad idea. Much better, a pretty standard approach, is to bring a copy of that entire user database into HDFS, right alongside your activity logs. Now you have both data sets sitting there in your distributed file system. Then you can use what are called sort merge joins, or sometimes reduce side joins. Here's how it works. The mappers process both data sets. They extract the user ID as the key from both the activity event records and the user profile records. The MapReduce framework then takes all these key value pairs, partitions them by the user ID key, and sorts them. This guarantees that all records for the same user ID, both the profile and all activity events, end up at the same reducer. You can even use something called a secondary sort. It's a clever trick to ensure that within each user's data arriving at the reducer, everything is perfectly ordered. Like maybe the user profile record always comes first, followed by their activity events sorted by timestamp. This sets up the reducer for extremely efficient processing. The reducer then performs the actual join logic. It just processes everything for that one user ID, which is now altogether, often entirely in memory. No more network requests needed at this stage. This leads to incredibly high throughput for joins across massive datasets. And this pattern is powerful because it cleverly separates the physical network communication and all that data movement from your actual application logic. It simplifies your coding and makes the whole thing robust against failures. You can think of the mappers as essentially sending messages to the reducers, where the key acts like the destination address.
That makes perfect sense. It really leverages that sorting mechanism. And it's not just about joining, it's also about grouping too, right? Like when you want to count how many times something happened for a specific user or sum up their purchases.
Exactly. Grouping, which is like the Drew PBY clause you see in SQL, follows a very similar pattern. Mappers emit the desired grouping key, and the MapReduce framework guarantees that all records sharing that same key are routed to the same reducer. This is exactly how you perform aggregations like counting records, COUNT, summing up values, SUM, or finding the top items within each group. It's also critical for something called sessionization. That's essentially grouping together all the clicks and actions a single user takes during one visit to your website, even if those actions hit different web servers. You group by user ID, maybe sort by time, and the reducer gets a complete, ordered picture of their entire session. Very useful.
That makes a lot of sense. But what if you have, say, a celebrity user, someone with millions of followers or interactions? Suddenly, all their data needs to go to that one single reducer, potentially creating a massive bottleneck, right? Slowing everything down.
You've hit on a classic and often painful problem called handling skew, or sometimes hotkeys. If one key, like that celebrity user ID, or maybe a very popular product ID, generates a disproportionately huge amount of data compared to others, then yeah, that massive chunk of data all ends up at a single reducer. This creates a hotspot that just takes way longer to process than all the others, slowing down the entire job. And since batch jobs are often chained, subsequent jobs that have to sit there and wait for this one slowest reducer to finish. It can grind everything to a halt. There are some clever algorithms to try and compensate for this skew. For example, some methods might sample the data first to identify likely hotkeys. Then during the join, the mappers can maybe send records for these known hotkeys to random reducers instead of just one based on the hash. But then you also have to replicate the corresponding records from the other dataset to all those random reducers. It gets complicated, but it spreads the load. Another strategy, particularly for grouping hotkeys, might involve a two-stage grouping process. The first stage groups on a random reducer just to compact the data for that hotkey, and then a second stage combines those pre-aggregated values. Now, while these reduce-side joins are incredibly versatile, they can be expensive because of all that network copying, sorting, and merging involved in the shuffle. If you can make certain assumptions about your data, map-side joins can often be much, much faster. The key thing about map-side joins is that they happen entirely within the map phase. There are no reducers involved, and no explicit sorting or shuffling across the network. Each mapper just reads its input block and writes its output file directly. One common type is a broadcast hash join. This works well if one of your datasets is small enough to fit entirely into the memory of each mapper task, say, a lookup table of product categories or country codes. Each mapper just loads that small dataset into an in-memory hash table at the start. Then, as it scans through its chunk of the large input dataset, it can simply look up the join key in its local hash table. No network communication needed for the join itself. You essentially broadcast the small dataset to all the mappers. What if both datasets are large, but they happen to be already partitioned in the same way? For instance, maybe both your user activity logs and your user profile data are already split into files based on the last digit of the user ID. In that case, you can use partitioned hash joins. Each mapper only needs to load the specific partition of the smaller dataset that corresponds to the partition of a larger dataset it's processing. This dramatically reduces the memory needed on each mapper compared to a full broadcast join. And finally, if the inputs are not only partitioned the same way, but are also sorted by the same join key within each partition, you can use map-side merge joins. Here, the mappers can essentially merge the two sorted input streams sequentially, just like the reducers would in a sort merge join, but again, without needing the expensive shuffle step. Optimizing for these map-side joins really requires having good metadata about the physical layout and properties of your datasets, how they're partitioned, how they're sorted. That's what tools like HCatalog and the Hive Metastore provide in the Hadoop ecosystem. It's all about working smarter with how your data is organized.
Okay, we've talked so much about how these systems work, mappers, reducers, joins, sorting. But what's the tangible output? What's the end game? What are all these massive batch jobs actually building for us behind the scenes?
That's a really important distinction to make. Unlike, say, online transaction processing (OLEP) systems that are designed for quick lookups of a few records for a user, or online analytical processing (OLAP) systems that typically produce reports and dashboards for business analysts. The output of a batch processing job is often not a report for a human to read directly. It's usually another system, another data set, or input for another process.
It's quite remarkable, actually, that one of Google's very first original applications for MapReduce is something we all interact with constantly and probably every day without even realizing it. Can you shed some light on that one?
Absolutely. Yeah, one of Google's original killer apps for MapReduce was for building its search engine index. I mean, think about what a search index is. At its core, it's a massive data structure, often like an inverted index, using something like Lucene, that efficiently maps keywords to the documents or web pages that contain them. It's a huge structured data set that needs to be constantly built and updated as the web changes. Google's original index was built using a workflow of, I think, 5 to 10 interconnected MapReduce jobs. Batch processing is incredibly effective for building these kinds of indexes, especially when you have large, relatively fixed sets of documents to process. Mappers can partition the documents, reducers can build the index for their assigned partition, and these immutable index files are then written out to the distributed file system. You can either periodically rerun the entire workflow to rebuild the whole index from scratch, or you can design workflows to build it incrementally, adding new documents or updating links. Another incredibly common output, especially nowadays, is key value stores that power machine learning and recommendation systems. Batch processing is perfect for training complex machine learning models. Think spam filters, anomaly detection systems, image recognition models, and especially recommendation engines. People who bought X also bought Y. The output of these often very complex batch training jobs is frequently a queryable database itself. For instance, a key value store where the key is a user ID and the value is a list of recommended friends, or the key is a product ID and the value is a list of related products. Now you might think, why not just have the MapReduce job write directly into my live production database? But as we touched on before, that's generally a really bad idea. It would likely be too slow, you'd easily overwhelm the production database with writes, and crucially, it would completely mess up MapReduce's all-or-nothing guarantee for output. If one task fails halfway through writing, you don't want partial, potentially incorrect data showing up in your live system. The much better solution, and a very common pattern, is for the batch job to build a brand new version of the database itself as a set of immutable files right there within the job's execution context. These complete new database files are written to the distributed file system, like HDFS. Then, these files can be loaded in bulk into specialized read-only query server systems like Voldemort, Terrapin, or ElephantDB were designed for this. Or you could use HBase's bulk loading feature. These servers can then atomically switch over to using the new files, ensuring consistency and making it trivial to roll back to the previous version if the new one has problems. This pattern really leverages the strengths of batch processing, Building indexes by extracting keys and sorting data is a very natural fit for the MapReduce model.
That's a really powerful pattern, building the whole output atomically. So there's a consistent philosophy emerging here behind how batch jobs produce their output, isn't there? It almost mirrors those Unix lessons we started with, this idea of immutability, replacing outputs rather than modifying things in place.
You've absolutely hit on a core tenet. Yes. The underlying philosophy is that inputs are treated as immutable. The batch job has no side effects except for producing its designated output. And that output completely replaces any previous output from a prior run of the same job. It doesn't modify existing state. This means you can rerun a job as often as you need to. Maybe the first run failed, maybe you found a bug in the code without messing up the system or corrupting downstream data. This leads to several really powerful benefits. First, if you introduce a bug in your code, you can simply fix the code, roll back to the previous good output, and rerun the job to generate the correct output. This idea of human fault tolerance is incredibly valuable. It actually speeds up feature development because it minimizes the fear of making irreversible mistakes. Second, if a map or reduced task fails mid-job due to hardware issues or whatever, the framework automatically retries it. And this is safe precisely because inputs are immutable, and any partial outputs from the failed task attempt are simply discarded. The retry starts clean. Third, the same set of input files can be used as input for many different jobs, perhaps for monitoring, debugging, or different kinds of analysis without interference. And finally, just like Unix, batch jobs strongly encourage the separation of the application logic from the wiring, how the data gets from one stage to the next. This really promotes code reuse. Although, unlike traditional Unix, which often relies on untyped text files, Hadoop and related systems typically leverage structured file formats like Avro or Parquet. These provide schemas and allow for much more efficient serialization and processing compared to just parsing plain text.
Okay, so MapReduce was clearly a game changer, incredibly powerful for its time. But, technology never stands still. What were its limitations eventually? And how did the industry evolve beyond just raw MapReduce?
Yeah, MapReduce was revolutionary, absolutely. But it certainly had its quirks and limitations. For one, writing code directly against the raw MapReduce APIs was quite laborious. It required a lot of boilerplate setup code, which made development slow and sometimes error-prone. And its execution model had some inherent inefficiencies. For example, it always sorted the data between the map and reduce stages, even if your particular job didn't actually need sorting. It also had to fully materialize all the intermediate data from the mappers to disk, on HDFS usually, before the reducers could even start. This led to poor performance for certain types of processing, especially multi-stage workflows where the output of one job immediately fed into the next, or for iterative algorithms where you're looping over the data. Even though it's worth noting, MapReduce was incredibly robust against frequent task terminations, which was a key design consideration back at Google given the hardware they were using. So to address these kinds of problems, a new generation of data flow engines emerged. Think Apache Spark, Apache Tez, Apache Flink. Their core idea was to handle an entire workflow, multiple stages of computation as one single job, rather than a sequence of independent MapReduce subjobs. They explicitly model the flow of data through the various processing stages, which are often called operators. These engines offer some significant advantages over that classic MapReduce model. Sorting is performed only when it's explicitly required by an operation like grouping or joining. They often eliminate unnecessary map tasks if data doesn't need transformation before a reduce-like operation. They can make more sophisticated locality optimizations, trying to place tasks that consume data on the very same machine as the task that produced it, sometimes even exchanging data through shared memory buffers, avoiding network hops. Intermediate state between stages is often kept in memory or spilled to local disk, rather than always writing it to HDFS with replication. This dramatically reduces I/O overhead. Operators can also start executing as soon as their input data starts becoming available, without waiting for the entire preceding stage to finish completely. It's more of a pipeline.
And they typically reuse Java Virtual Machine JVM processes across multiple tasks within a job, which cuts down significantly on the startup overhead that could be quite noticeable in MapReduce. Fault tolerance in these newer data flow engines is handled a bit differently too. Since they often avoid writing all that intermediate state to a distributed file system like HDFS, if a machine fails and some intermediate data partition is lost, the engine typically recomputes just that lost partition by rerunning the necessary tasks from an earlier stage or even from the original input data. This relies heavily on the processing operators being deterministic, meaning they always produce the exact same output given the same input. Spark's RDD lineage and Flink's checkpointing mechanisms are based on this idea. It's generally a more streamlined and often much more efficient approach, especially for complex workflows.
That makes sense for more sequential pipeline-like data flows. But what about data that's inherently graph-like? Social networks, web links, dependency graphs, where the relationships between entities are the key thing and the processing is often iterative. That seems like a different kind of beast entirely.
You're absolutely right. It is. Many important graph algorithms think about PageRank for ranking web pages, or finding connected components, or calculating shortest paths are inherently iterative. They typically involve repeating a calculation across the graph, refining the results in each pass until some condition is met or the values converge. Raw MapReduce is pretty inefficient for this kind of iterative work because, as we said, it tends to reread the entire input dataset and produce a completely new output dataset in each and every iteration, even if only a small part of the graph actually changed or was affected by the computation in that round. Lots of wasted I/O and computation. This inefficiency led to the development of specialized models for large-scale graph processing, most notably the Pregel model, which Google developed internally. This model has been implemented in open-source frameworks like Apache Graph, which runs on Hadoop, and also integrated into broader dataflow engines like Spark's GraphX component and Flink's Skelly library. In the Pregel model, the computation revolves around the vertices, the nodes, in the graph. Computation proceeds in rounds, or supersteps. In each superstep, a function is executed for each active vertex. This function can receive messages sent to that vertex in the previous superstep. It can modify the vertex's state, and it can send messages to other vertices, usually along the graph's edges, which will be delivered in the next superstep. Crucially, a vertex remembers its state in memory between these supersteps. So if a vertex doesn't receive any messages in a superstep, it might become inactive, and no work is done for it until it receives another message. This makes it very efficient for algorithms where activity is sparse and localized in the graph. It's a bit like the actor model of concurrent computation, but adapted for distributed batch processing with fault-tolerant, durable storage of vertex state and messages delivered synchronously in these fixed rounds. Fault tolerance is typically achieved by periodically checkpointing the state of all the vertices to stable storage. The main challenge with distributed graph processing, though, is often the high volume of cross-machine communication if the graph is partitioned poorly, and the intermediate state, messages and vertex states, can sometimes become even larger than the original graph data itself. For this reason, if your graph actually fits comfortably in the memory of a single powerful machine, a highly optimized single machine graph processing library might actually outperform a distributed batch process. Distribution isn't always faster.
Okay, this is incredibly powerful stuff, clearly. But for someone listening, trying to get well informed, diving into raw MapReduce APIs or trying to understand the nuances of skewed joins versus broadcast joins versus partition joins, it sounds like a huge undertaking. Are there easier ways to leverage this immense power without having to become a low-level distributed systems expert yourself?
Absolutely, yes. The industry very quickly recognized that writing raw MapReduce code was indeed quite laborious and error-prone. So pretty early on, higher-level APIs and languages were created on top of MapReduce to abstract away a lot of that complexity. Tools like Pig with Pig Latin, Hive with HiveQL, which looks like SQL, Cascading, a Java API, and Crunch, another Java API, made MapReduce much more accessible. And the newer dataflow engines like Spark and Flink came with their own powerful high-level dataflow APIs right from the start. These are often inspired by functional programming concepts and relational algebra, offering familiar operations like joins, grouping, filtering, aggregating, mapping, and so on. These higher-level APIs significantly reduce the amount of code you typically need to write, and they also often enable more interactive use cases, like exploring datasets using a shell or a notebook interface, which beautifully aligns with that original Unix philosophy of experimentation we talked about. The really big shift, though, has been increasingly towards declarative query languages, especially SQL or SQL-like interfaces. When you specify your data transformations declaratively, for instance, just stating what joins are required between which data sets using SQL syntax, powerful query optimizers built into systems like Hive, Spark SQL, and Flink SQL can automatically figure out the best way how to execute that query. They analyze the query, look at statistics about the data, like sizes, cardinality, data distribution, and use cost models to choose the most efficient join algorithms. Maybe a broadcast join here, a sort of merge join there, optimize the order of operations, push down filters, and so on. This means you don't necessarily have to be an expert in all those different physical join algorithms we discussed. The system tries to figure it out for you. Now, while these systems incorporate more declarative SQL-like features, they crucially still retain the flexibility to let you drop down and run arbitrary code, like user-defined functions in Java, Scala, or Python, for things that don't fit neatly into the relational model. Think complex machine learning algorithms, specialized text processing, image analysis, or other custom business logic. That's a key difference from traditional databases. They also employ advanced execution techniques under the hood, like vectorized execution, processing data in batches rather than row by row, and even runtime code generation for simple operations, which allows them to crunch through data much more efficiently than just running general-purpose interpreted code. So ultimately, yes, modern batch processing frameworks are increasingly looking and feeling more like traditional massively parallel processing, MPP, analytical databases, offering declarative power, sophisticated optimization, and SQL interfaces. But they achieve this while simultaneously retaining the fundamental flexibility and extensibility of their processing engine roots, allowing them to handle a much wider variety of data types and complex processing tasks that go far beyond just standard SQL analytics.
Wow, what a journey indeed. From, humble punch cards and those surprisingly simple, elegant Unix commands, all the way to these massive, complex, distributed systems that are powering everything from your search results to your personalized product recommendations. We've really seen how those core ideas, doing one thing well, composability, clear data flow, have not only endured but have been evolved and scaled up to handle truly mind-boggling amounts of information.
It's a fascinating evolution, isn't it? And at its heart, batch processing, as we've defined it, is characterized by its bounded, immutable inputs and its derived, often atomically produced outputs. The progression we trace from simple Unix tools through the distributed brute force of MapReduce and now to these more sophisticated data flow engines really showcases a continuous effort to improve how data gets partitioned across machines and, crucially, how faults are tolerated gracefully in these very large-scale systems. The enduring power, I think, lies in that ability to separate your core application logic from the underlying complexities of distributed data movement and vault handling. And also in the sheer reliability you get from producing atomic, fault-tolerant outputs that can be easily rolled back or retried if things go wrong. This whole approach allows developers to tackle incredibly complex data problems with a scale and a level of flexibility that just wasn't possible before.
It really is incredible when you think about it how these systems, even when faced with potentially constant failures across hundreds or thousands of machines, can still guarantee a correct, consistent output at the end of the job. It's a level of reliability and data integrity that, frankly, goes far beyond what we usually expect or even achieve in typical online request response services.
Exactly. And that remarkable reliability comes directly from that core assumption we've discussed throughout, that the input data for a batch job is bounded. It has a known, fixed size, a beginning, and an end, and therefore the job eventually completes, producing its final output. But
Mhm.
what happens when the data never stops, when it's not a bounded file or data set, but an unbounded continuous stream of information constantly flowing in? That's where stream processing comes into the picture. And, well, it fundamentally changes quite a lot about how we need to think about and build these data systems.
And that, my friend, sounds like a fantastic dup dive for another day. Thank you so much for joining us on this exploration of batch processing. We really hope you, listening in, feel a little more well-informed now and maybe even a little surprised by the hidden power and the fascinating history behind some of the largest, most reliable data operations happening in the world today.